Hi everybody, and welcome to this talk about complex functional maps. We will talk about how to link tangent bundles in a conformal orientation-preserving way. This is joint work including myself, Etienne Cormand, Simone Merzi, and Max Ovzhanikov. Our main focus for this talk will be shape matching, which is the study of maps between shapes. Well, two volunteers have accepted to act as 3D shapes, Mr. Cow and Mr. Fox here. A map takes a point on the source shape and sends it on the second shape. Our goal is to compute maps between shapes. There are many candidates, such as this non-injective map or this map with strong metric distortion. You see that the distance between this pair of points gets reduced by the map. Well, we want to compute natural maps. In other words, maps with desirable properties such as bijectivity, so not the first map, and isometry, so not the second map either. We need a way to compute maps while enforcing these desirable properties. For instance, we could design this energy, which is low for near isometric maps. But remember that Mr. Cow and Mr. Fox are defined with many points, thousands for reasonable discretizations. The space of potential maps is thus huge and quite difficult to explore. We need a relaxation of the problem. One possible solution is to match not points, but functions between shapes. This is a more general setting since we can match directs to get back to the initial problem. The key advantage of matching functions is that the resulting mapping between functional spaces, matching functions, the resulting mapping is a linear map. It's called the pullback, and as a linear operator, it can be decomposed in a linear basis. It is then common to use the Laplace-Beltrami operator eigenbasis, which is the equivalent of a Fourier basis for curved domains. In particular, it can be ordered from low to high frequency. Any smooth function can be decomposed in this basis. I hope everyone's with me. We can decompose both source and target functions in respectively source and target Laplace-Beltrami eigenbasis. Now, cutting out high-frequency information, we can squeeze the important parts of our functional mapping into a small matrix, typically 30 square. This matrix is called functional map and simply contains the important information of a smooth map between two shapes. Besides, a near isometric mapping will take the form of slanted diagonal, like this. Why is this useful? Well, we went from thousands of parameters, pointwise maps, to less than 100 small matrices. That's perfect, that's great. Now let's get back to our goal. Remember that the goal was to compute maps. Now that we have a compact way to write these maps, the question becomes, how do we compute functional maps? Then, given a functional map, it is easy to come back to pointwise maps, right? We match directs. So, how do we get these functional maps? One idea is to use landmark functions, also called descriptors, to guide the map, since these descriptors need to correspond via the map. Adding some constraints like isometry, we end up with a least squares problem. So that is the landmark functions, that is the energy to promote isometry, to end up with a near isometric map, and boom, the resulting system is a least squares problem that is easy to solve, and we get the map. The thing is, there are still many map candidates. For instance, let's consider these two, the ground truth to the left, which is the map that we want, right? And on the right, the left-right symmetry. Notice how left and right are exchanged when going from Mr. Cow to Mr. Fox. The functional map pipeline only uses intrinsic information, which is a way to say that it does not use embeddings, but just edge lengths. The problem is, both these maps candidates are valid from the intrinsic point of view, because both matrices, to encode these maps, as you see here, well, they are slanted diagonal, so it means that they encode a near isometry. Well, yet, we would like to have a possibility to rule out this left-right symmetry with the encoding of the map. And meaning that we don't want this left-right symmetry to have a nice encoding like this. And one interesting remark that we could make at this point is that the first map, the ground truth, is orientation preserving, while the other one reverses orientation. I'll come back to this and why is that? Our idea is to incorporate orientation information into the functional map pipeline. More specifically, our contribution is to propose complex, our contribution is to propose complex functional maps, an orientation-aware encoding for maps between shapes. Notice that for a symmetric map, the functional map is slanted diagonal, while the complex functional map is basically noise. Indeed, our complex functional maps can only encode orientation-preserving maps, like the ground truth in this case. Now, some of you may be wondering, like Mr. Cow here, how do complex functional maps work? Let's start at the beginning, with tangent bundles. In our case, the tangent bundle of a shape is the union of all tangent planes of that shape. A tangent plane at point P is represented here. It can be oriented with inner or outer normal on a closed shape. Following the usual rule, outer normal will correspond to counterclockwise rotation on the tangent plane, and inner normal will correspond to clockwise rotation. Any tangent vector at point P basically lives on this tangent plane. Now, we can explain a bit more why we said earlier that our left-right symmetry was orientation reversing. Well, it's simply because it flips tangent planes, changing outer normals into inner normals, and thus reversing orientation globally on the shape. So, tangent bundles are oriented. Now, what lives on tangent bundles? Tangent vector fields, right? Tangent vector fields are simply one tangent vector per point, and we want it to be smooth. That's basically the definition. The idea is now to match not functions. Remember that function maps, we didn't want to match points, but functions, but now we don't want to match functions, but an even more complex object, which is tangent vector fields, because they carry orientation information. So how do we do this? We use the map differential. The right object for this is the map differential, like I just said, also called push forward, which is the best linear approximation for the map at point P. The map differential links the tangent plane at point P and the image tangent plane at point phi of pi, with phi is, where phi is the map itself. For instance, given a curve on source and its image and target, both velocities at point P live respectively on source and target tangent plane, and they are linked by the push forward d phi at point P. The push forward d phi thus links source and target tangent bundles. In other words, it takes as input tangent vector fields on the source shape and yields tangent vector fields on the target shape. The important property of a push forward is its linearity. As a consequence, the push forward is an R2 tensor field, which is 4 parameters per point. Now let us look at the differential of a conformal map. What are conformal maps? They have the nice property of preserving angles. So, given two vectors on the tangent plane, alpha the angle between them, their image by the map differential will have the same angle alpha between them. This is conformal. What that means for our differential is that it cannot shear the tangent plane. It can only scale, rotate, or flip it. Now, if the map is also orientation preserving, then the push forward at point P is simply a rotation and a scaling. It cannot flip the tangent plane. So it takes the form dp of phi is a rotation, or theta, and a scaling, rho. What is more, by parametrizing tangent planes as complex instead of R2 spaces, we can then write the differential at point P as a simple, complex multiplication. In other words, the differential of a complex orientation-preserving map is complex linear. So, a conformal orientation-preserving map differential will thus be C-linear, which is a strong property. It adds up to being R-linear, which was the property for map differentials. Now we have conformal map differentials, and they have C-linearity. This property corresponds to the Cauchy-Riemann equations, and it is true for the map differential if and only if the map is conformal and orientation preserving. Cauchy-Riemann equations, phi is conformal and orientation preserving if and only if we have these Cauchy-Riemann equations. And to conclude, as I said before, but now we say it again because it's important, the push forward of a map is complex linear if and only if the map is conformal and orientation preserving. Now, as a complex linear operator, it could be also decomposed in a basis, a complex basis. For this, we use the connection Laplacian operator, which is the Laplace operator for tangent vector fields. Remember that since we use C encoding for the tangent spaces, the tangent planes for each point, the smooth tangent vector fields are encoded as complex valued functions. So the connection Laplacian is a sort of complex operator, an operator for complex functions. And we will use this operator for, remember these functions that we had for the Laplace-Beltrami operator, this eigenbasis? Well, now boom, we have the same eigenbasis for tangent vector fields. And we can use this eigenbasis to decompose any smooth tangent vector field in this basis. Great. Now, just like for functional maps, we can encode any conformal orientation-preserving map as a small complex matrix that we call complex functional map. For functional maps, the question remained that we needed a way to compute the functional map. Here, we will not reinvent the functional map pipeline, but rather plug our complex functional map extension to it. We will compute a complex functional map from a functional map. If the map can be encoded as a complex functional map, then it means that the original map was, well, conformal, but more importantly, orientation preserving. I hope everyone is still with me. It is almost over. To link functional and complex functional maps, we use a definition of the push forward stating that functional spaces and tangent bundles must correspond under the respective actions of the map and its differential. We get the following equation, and we use it to, if we have the functional map C as input, we write this equation, which must be true for all tangent vector fields, and we can write an energy using this equation. Obviously, we cannot write it for all tangent vector fields, but we simply ensure that this energy is as low as possible for all these vector fields xi, which can be, for instance, the connection Laplacian eigenbasis, which covers all smooth tangent vector fields. The resulting system is easy to solve because the unknown is a small complex matrix and because it is a least squares problem. And we retrieve this small complex matrix Q, which is our complex functional map. Remember, the encoding for conformal, orientation preserving differentials. Let us come back to our left-right symmetry. Now we understand why our encoding for the symmetric map gives noise. Indeed, the left-right symmetry could not be encoded as intended because it's not orientation preserving. So the complex functional map extracted from the functional map of a symmetric map is basically noise. It cannot be encoded. Even more interesting, let's say that we have a mixture of both ground truth and symmetry as input functional map. This is the third column. This third functional map is what we call symmetry blind. As you can see, the recovered pointwise map on the right mixes, well, left and right side of the shapes. However, our algorithm still retrieved the part of the map that was orientation preserving, right? Because it's exactly the only part it can encode as a complex functional map. It is also the part that we wanted to keep. To sum up, complex functional maps help regularize functional maps towards orientation preserving maps. Now, how well do complex functional maps work in practice? Glad you asked, Mr. Cow. A first advantage of complex functional maps is that since they encode differentials, they allow for efficient tangent vector field transfer, here visualized with their flow. Our method proves faster and more robust to various kinds of noise compared to other methods. Also, as advertised a few slides back, it can also be plugged into functional map pipelines to make it orientation preserving. The protocol is very simple. Once the functional map is computed, for instance from descriptors, then one can estimate the complex functional map from the functional map and only then retrieve correspondence, because computing the complex functional map first helps making the map orientation preserving. Now, even if the input function map was a mixture, the complex function map will only retrieve the orientation preserving part, which makes the general pipeline stable under symmetry aliasing. As a result, when estimating maps from intrinsic symmetry blind descriptors as WKS, wave kernel signature descriptors, we get this. So from maps that completely mixed symmetries or yielded bad results, we get maps close to ground truth. We can also plug our complex functional map addition into pipelines that don't involve descriptors, such as refinement pipelines. For instance, we have this zoom out or follow-up refinement pipelines, and we can plug our method, our complex functional map addition, into them, and we get also better maps that are closer to ground truth, and they help deblurring the general pipeline. Well, this concludes our talk about complex functional maps, a way to make the functional map pipeline orientation preserving. Thank you all for listening.